So welcome everybody. So I make a living these days helping organisations to transition to continuous delivery, and I think continuous delivery is an important thing. And I often get to a stage where we're in a conversation where I'll say, "Oh yeah, okay, we understand how that can work for code, but you can't do that for data." And actually, yes, you can. And in order to deliver continuously, you kind of need to. So that's really what my talk is about. So I want to talk a little bit about the thinking and some of the techniques and approaches for dealing with data. So this is probably what I would think of as kind of a design level technical talk. So I'm not going to talk about code, but I'm going to talk about design ideas and some patterns for handling data migration problems and those sorts of things during the course of this talk. So if I can get it so the chat screen changes. Can everybody see my screen okay? Yeah, just nod if you can, that'd be good. Thank you. Right, so what is it that we're trying to achieve with continuous delivery? So the way that I like to describe it is that we're trying to optimize from having an idea to getting useful software into the hands of users. We're trying to do that repeatably, reliably, and to really qualify, to my mind, for continuous delivery, you probably need to be able to do that multiple times per day. And so that's challenging. There's a lot going on. There's an awful lot in terms of the processes that we need to optimize. Continuous delivery for me is not just about deployment automation. It's about working in a way so our software is always in a releasable state. One of the ways that tools that you can use to drive that is the idea of cycle time. And cycle time is kind of like a die trace analysis of your development process. If you imagine making a single line change to your production environment, your production system, what would it take for that change to pass through all of the normal steps in your software development process? Somebody would need to identify that as a need. Somebody would need to capture that as a requirement in some form. Somebody would need to allocate that to a team or select it for a team. Somebody need to turn that into something that you can start working on and building, and somebody need to write some tests and deploy it, and so on and so on and so on. So there are all these steps, and you can use cycle time as a measure of the efficiency with which you're able to approach that. I'm showing here two cycle times from projects I worked on. The top line is from a bank system. It was database centric in this system, but they couldn't make a single line change to their production environment in under 103 days. The bottom one is a picture of the process involved in delivering one of the world's highest performance financial exchanges. This is about 15 or 20 times bigger and more complicated. We could evaluate any change to our production system, including any change to the data, and get an answer back. Is this releasable in under an hour? So those are very, very different kinds of experiences. We use ideas like the deployment pipeline to automate the route from change to releasable outcome. And that is the scope of a deployment pipeline. And so if we're trying to get to this releasability, then data is part of the statement of releasability. We can't make changes only to the code that are out of step with the data that the system processes and consider that to be releasable. So as I said in passing, one of my favorite sound bites for continuous delivery is working so that our software is always in a releasable state, and the scope of a deployment pipeline is everything that is required to achieve releasability. So keep that in the back of your mind as we're going through and start talking about data in more detail. So let's start thinking about some of the fundamentals of what that would take. So the first thing is that we need to version control everything. If we're going to be able to achieve the repeatability and reliability of being able to create releasable things multiple times per day, we've got to have a great statement on automation. So we're going to version control pretty much everything. We're going to make changes in small steps. That's a way of reducing risk, simplifying the changes and making them easier to evaluate. And that also allows us to test pretty much everything. And finally, we're going to design in order to support ideas like data migration. This isn't something that happens by accident. This can be sometimes a more difficult retrofit to an existing system. There are some techniques to achieve that, but it's more complicated for existing code. But certainly when you're starting something afresh, designed from the outset to support ideas like data migration. So what is it that we need to version? Well, we need to version the code that we could create that interacts with our stores of data, for sure, and everything else. We want to version control pretty much everything within the scope of our system. One way to think about this is ideas like infrastructure as code. If anybody is interested, I have a YouTube channel, and last week's video was about infrastructure as code, which goes into the details of version controlling some other aspects of the system that are kind of interesting. But we want to version pretty much everything. And the data needs versioning too. It's not really continuous delivery if we can't release because our schema has changed or the content of our data has changed in some way. So what do we mean by data? I think to paraphrase, it's somebody kind of turtles all the way down. It's all data really, but in this context, what we're really talking about is the data that's deployed at release time and that which is generated at runtime. Those are kind of different things. And it's easier to think about sometimes the data that we deploy at release time, the code and the configuration and static data and all that kind of stuff. But the stuff that's generated at the runtime of our systems is a bit more complicated and a bit more problematic. That's the stuff that I'm really focusing on largely in my talk today. There are some grey areas that I point out here that are kind of crossing the boundary between the, which category does reference data fall into, which runtime configuration. We'll talk a little bit about those towards the end of the presentation. So there's data in different contexts that matter. So there's the data in production for sure, but there's also data that supports automated testing of different kinds, automated that supports manual testing, performance testing, migration testing, and we need to take all of these seriously. If we really want to take control, then we've got to think about managing all of these sets of data effectively and efficiently with high levels of automation. I think that there are two facets that are important to think about when we think about data, and it's usually easiest to think about these in the context of relational databases. So forgive me if I tend to use the terminology of relational databases, but try and keep in the back of your mind as I'm going through this, that these ideas are not only applicable to relational databases, they are applicable to non-SQL data stores of all kinds. I've done this with some weird kind of data stores as well as relational databases. Relational databases sometimes just make the tooling a little bit easier. But all data, even in a non-SQL database, has records of some kind and a structure that matters of some kind, even if that structure is implicit rather than explicit. And we need to think about those two different facets of the data separately to one another. So let's start thinking first about the slightly simpler case of structural changes to our data. The structure must be allowed to evolve. I think that one of the things that we have learned about software development all of the time is that we are extremely unlikely to get things right first time. Software development is an exercise in learning and discovery, and not perfect prediction. So we need to allow ourselves the capacity to learn and adapt our software systems. That means that the structure must be allowed to evolve. Fred Brooks famously said, as soon as one freezes a design, it becomes obsolete. If we don't want our data structures and data stores to become obsolete, we need to allow them to change. And therefore, we must consider the migration of data. If we are going to change the structure of our data, we've got to consider how we're going to deal with records stored in the old versions of the structure, and how we're going to cope with those. We have to take those ideas seriously. For structure to evolve, here are a few tips to think about. The first one, and probably one of the quickest wins, is to try and adopt the discipline of making additive changes. Try and structure data so that you are largely just adding things to the data. This is true both at the structural level, but also at the record level. If you can, instead of deleting, a record from a database, if you can mark it as deleted, that gives you some more flexibility, some more opportunities to do cleverer things with the data over time. These days, storage is so cheap that storing stuff that is deleted and marked as deleted is not usually a big overhead in terms of cost, and so is worth considering. Next, if we want our structure to evolve, we've got to version control the structure scripts themselves, migration scripts, Delta scripts. We've got to version control everything. I think that the idea that we should be working to adopt is that there is no manual intervention directly with the data in production. All changes go through some kind of automated script and therefore can be version controlled. It's not acceptable in a continuous delivery kind of model, really, to have somebody with an admin console or similar going in and tinkering directly with these data stores, because that makes the chances of other forms of automation working less likely. So we want to version control all of these things. We want to reduce to the point of eliminating manual intervention, direct manual intervention with the configuration and setup of our data in production. And we are going to make those changes through scripts and version everything. We're going to create it. That gives us the opportunity then to test the migrations and validate the changes before we apply those changes. We can write automated tests that allow us to check that our migration scripts or structure change scripts are effective. And we can use database refactoring techniques. I'm going to give you a reference to a book at the end of the presentation that describes what I'm talking about in much more detail than I'm going to go into. So let's start thinking about that in a bit more detail and think about versioning schema changes. Schema version, it should be based, every schema change should be versioned and based on a monotonically increasing sequence number. So each delta ticks the sequence. That way we can uniquely identify a change in structure, and we know what sequence those changes need to be applied. Store the desired schema version with the application. So the application has a record of which versions of the database schema it can work with. Store the current schema version with the data. So in the data, wherever that is, a table in a relational database or something like that, there's a reference. And then we can automate the comparison of, does this version of the application work with this version of the schema? What migrations would I need to apply to this version of the schema to get them working together, and so on. So let's start visualizing this in a little bit more detail. So my little purple blobs on sticks represent an application of some kind, and my little grids on sticks represent a data store of some kind. And for them to do useful work, there's going to be some kind of relationship between those two. There's a dependency between those two. If we change either one, we need to be certain that they are going to work together. We also need to know, so we need to have somewhere have a record of which version each of these things is at and which versions work together. And so part of treating this stuff seriously is to track that, track that and, again, automate it as far as we can. We need to understand which relationships work and which relationships don't. So somewhere or other, there needs to be a record that's the equivalent of this. We're saying version I works with version N. That's good. And version I also works with version N+1. That's good too. And so on. And we keep that record somewhere. We need to track that information. Now, if these two things are changing independently of one another, that's a dependency management headache. That's a problem. So the simplest route to doing this is to version control these things together. Always change them in step. This tends to push you in the direction of ideas like more like microservices, where the applications and the data that support them are versioned together and changed together. If you are using data stores as an integration mechanism, which is a common pattern for more traditional organizations, one, that's a little bit of an anti-pattern. That's a little bit fragile in terms of the way of working. And two, it adds to the complexity. Now you have to do extra work to encode that map of which versions of the application work with which versions of the data. So simplest thing of all is to just version them all together. So we put them all in a version control system. Every time we change either one, we just commit that to our version control system. And now we've got a one-to-one relationship between the application version and the data version. And that's kind of almost impossible to go wrong at that point because we've kept them together. Now, you don't always have the freedom to do this. So this is just one route. But where you do have that freedom, it's a great one to take advantage of. It's the simplest route forwards. That isn't all there is, though. It isn't just about the schema. If we're allowing changes to be made to the schema, we must also then cope with this data that is stored in those schemas. And so we need to think about data versioning, not just data schema versioning. In this model, we need to think about the structure of the data itself, and we've got to think about having a path from between versions of the schema for the data that those versions of the schema contain. We need migration scripts. We need to be able to migrate the data as we make those changes. So a good pattern for doing this is to start thinking about how we're going to capture that. So let's imagine some people that are making changes to either the application or the data schema. And so you're going to make a change to the application and the data schema together, or maybe you're going to change one of them independently of one another. And what we require them to do is every single time that they make such a change, that changes the schema of the data. They capture that in a little data migration script. So along with the schema change, in the same commit that changes the schema, you also include a little script that describes how data that's already in the old version of the schema should be migrated to the new version of the schema. And you capture that as a little delta script. And you version control all of those together. So you version control the schema change scripts and these delta scripts along with application changes. And again, you've got the one-to-one relationship. You know that all of these things, so that you, for any given change set in your version control system, you've got a definitive statement of which things all work together. So then we can kind of record each of these things in turn. As the changes happen and during development, we can kind of capture a series of changes and build up a list of these delta scripts. This doesn't imply that we must release for every one of these changes. That's optional. We can decide when we want to release. But the series of steps that it takes between releases is captured in multiple delta scripts. This kind of also decentralizes the approach. If a software developer decides that they need to make a data change, they just write the script to make the change and migrate the data as part of making that change in the application. And so that allows them to move forwards without heavy coordination between teams and so on. Again, we version all of these things together. So what does one of these things look like? So let's dive into one of these Delta scripts in a bit more detail. So we're going to have a script that represents the change in data structure. And then we're going to have a separate script or scripts that describe how to move the data from the previous version of the data structure to the new version. And then we're going to have a bunch of tests that evaluate the migration scripts. They check to see that those things can migrate test data as you're expected to. Well, when I practiced this when we built our financial exchange, we did kind of test-driven development for these migration scripts as part of the development of our data-centered, data-oriented changes. And then we version all of these things together, so we keep them all in step. So how does that work when we start to deploy? So we've got this stuff in version control system, and we've got a target environment. Remember, I said that our application keeps track of which versions it's at. In this case, the newest version of the Delta script is 80 for this release candidate, and the test environment is at 79. So at deployment time, then we're going to take the one outstanding change, and we're going to apply that to the deployed environment. We're going to run that Delta script, and that's going to update the schema, and it's going to migrate any data that's in that database to the new version. If we have a production version, maybe that's a little bit further behind. Maybe we're not deploying as regularly as we are to a test environment. And so come deployment time, our deployment tools will say, production system is at version 76. That means we need to replay deltas 77, 78, 79, and 80 in order to get production up to the same version that this release candidate requires. And then we're good to go. This is an effective deployment time strategy for migrating data. It might make you nervous thinking about this and thinking about the ability to undo. So there's one further step that you can take, which is to, at the time when you encode the roll forward script, the Delta script, you also encode an undo script. How do I step back from version 78 to version 77? Well, I run undo 2 in order to do that step back. You've got to remember what I said before about additive changes. You've got to be careful about the kind of changes that lose information in this process. So additive changes help, but this strategy allows a data store to be made to match any release candidate. You can kind of roll it forward through a sequence of deltas or roll it back through a sequence of undo scripts to match whatever a given release candidate needs. In practice, most of the teams that I know start off doing all of this work, and at some point, certainly the teams that I've worked with have become a little nervous that they weren't running the undo scripts ever, and therefore a little nervous about whether they worked. We still did test-driven development for the undo scripts as well as the Delta scripts, so they should have worked, but because we didn't try them on production data, we became a little bit nervous, and we eventually got to the point where we decided not to do the work to do the undo scripts. But that's a choice. If you want to be more thorough, give yourselves more options, doing both the roll forward and roll back scripts is a good strategy. And then you can kind of apply the undo script and roll back to whatever state you want the data to be in, again, to match the needs of the release candidate. There's a couple of tools that I can point you to that will help you to implement that strategy. One of them is open source, Flyway DB, and the other one, Redgate, do commercial tools for Microsoft family databases, and including these kind of roll forward and roll back techniques, as well as some other migration techniques that they support. Right, so that's an effective strategy for being able to manage the relationship between an application and its data store at deployment time. There's a bunch of other data migration patterns, though, that are useful in a variety of circumstances. So I'm just going to go through those a little bit. So the first one is I should say that these are patterns that I've identified and named. These are not probably generic names, but these are my patterns that I've spotted and named. So the first one's lazy reader. So the system can always read old versions of the software. Every record in the data store is versioned, and when a record is accessed, a suitable reader is selected, and the reader then presents a constant, up-to-date interface to the system, whatever the internal data structure. This is a useful implementation and is best coped with as a strategy pattern to plug in the readers and using the schema version as the key to identify the appropriate reader. This is most useful for very, very large data sets. When we built our exchange, we used to record in the territory of about 1 terabyte a week of data that we had to keep for 7 years. There's no way that we could afford the time to migrate all of that data. So if for any reason we needed to change it, the structure of that data, we maintained it as a stream, and then we maintained a collection of these readers that we would select at runtime based on the version of individual records. Now, there's a downside to this. It adds runtime complexity. There's a significant maintenance overhead for the readers, but it allows you to cope with massive data sets. It's also a good strategy for hot deployment. You can deploy on the old data set, everything's going to keep working. And it's still going to translate. It's very scalable, can cope with massive amounts of data. Next, lazy migrator. In this pattern, the system can read old versions, but it can also write out new records, new modified records. So each record is again versioned. When a record is accessed and is an older version, a migrator is selected that is able to translate from that old version to the current version, and it will write out a current version of that record. Again, this is best implemented via a strategy pattern using schema version as a key to identify which migration strategy to pick. This is very good in hot deployment environments with very large data sets. It's not quite as scalable as the previous one because you've still got to write out the data. It's very good for hot deployments. It's scalable. Translation cost is on read and is so spread out in the natural operation of the application. Migrations can be chained together to reduce the code maintenance overhead a little bit. The system is eventually consistent. At any given time, you can't guarantee that all of the data is in the same shape. This adds, again, runtime complexity. It's not clear when migration is, it's not always clear when migration is complete. And the maintenance overhead is fairly significant to manage the collection of migrators. But it's a useful pattern in some circumstances. Next, downtime migrator. The system can read old versions and write out new, as before. Each record is once again versioned and has an ID, so a version number, so we can kind of know what version it's at. Old records are found and migrated when the system's not busy. So it kind of, during downtime in the system, it just goes on in the background and starts looking for things work to do to migrate. So best use case, again, this works nicely with medium to large-ish data sets and hot deployment where you want to be doing live deployments. It's very good for hot deployment. It's scalable. You reduces system downtime. You can discard translators once there are no more records for that particular translator to translate. Once all of those versions have been migrated, the system is eventually consistent again with respect to data, and again you can chain migrations to limit the maintenance overhead. The downside, again, runtime complexity. It may be inappropriate for vast data sets because you may end up with kind of trawlers going and doing migrations forever. Migrations on top of migrations start to make you feel a bit nervous after a while, and you're not quite sure what's going to happen, and so you need to worry about that kind of problem, which is why the kind of data size limits, at least that's my level of nervousness with this approach. There's a significant maintenance overhead. Once again, need to maintain a collection of translators for every version to the current state, and that can be a lot of work for some kinds of systems. The one that we've already talked about is deployment migrator, and that's the pattern that we described with the diagrams. At deployment time, the system migrates all old records. The advantage of this is that it's the easiest one to understand. It's what tends to spring to nearly everybody's mind when they think about data migration. It can be implemented as a startup behavior of the system or as a deployment time behavior of deployment tools, and so it's easy to think about. The downside is that it's tricky to test. These migrations can become very complicated over time, and it can be very, very slow. If you are employing the strategy that I described at the start, this deployment migrator pattern, then you should do some kind of scale test before you deploy to figure out whether some of your deployments are going to become very costly. They might incur significant downtime in their own right for some applications, and then you might need to think about adopting one of the more complicated patterns that I've described. They generally require significant application downtime in order for the migration to happen. You need to stop data access while you're performing the migration. And so speed of the migration is important. These are not ideal for frequent continuous delivery style deployments, really. They can be useful. They can be useful in many scenarios, but you need to treat them with a little bit of care because of these reasons. Test migrations, not state. When we start thinking about testing our data migration, what most people do is that they write a test for the end result, for the outcome that they're trying to achieve, that the database stands up in a particular state. I would advise that you don't do that. Instead, aim to test the migration, the code in your migration script. Think of your test as that. You're validating that your migration script does the things that you think it should do. That means that these tests are easier to chain together and easier to use. They are more flexible and more efficient. Migration testing is different to regular unit testing in a couple of ways. In continuous integration, we have all of our code at a known version on checkout, and so we can run all of our tests against that version. And that gives us a lot of flexibility to optimize the performance of our testing by parallelizing things. For migration testing, we're limited to the degree that we can do that. Migrations, we have a sequence that is imposed upon us, and it matters that we stick to that sequence. So the pattern for migration testing is that we're going to check out a release candidate with some migrations. We're going to apply the first migration and test that that's working, and then we're going to apply the second migration, and then we're going to test that that's working, and so on and so on and so on. We need to do these things in order, in the order in which they were created, and maintain that sequence for this testing to make sense. We'd like to be able to run our tests anywhere. And so the test data is important and the management of that. In general, my advice for a system that we want to test is to try and keep that system what I call a neutral state. What I really mean is as empty of data as we can. We don't want to be carrying around megabytes or gigabytes of test data with systems in order to be able to test them. We'd like to be able to update that data. It's also a slippery slope where tests are often coupled to one another through the data. So we'd like our tests on the whole to be generating data that they can use. So data defining the system undertakes data in a test that's for a system under test falls into three broad categories. We're interested in the transactional data, the data that is generated during the normal operation of the system. We're interested in reference data, sort of lookup information, and we're interested in configuration data. And then there are three different strategies that we can apply. We could use production data, we could generate that data within the scope of a test, or we could use what I call versioned test data, which means I know that I'm running in an acceptance test environment, and that acceptance test environment has a predefined set of data that needs to be deployed for the tests in that environment to work. So let's just think about which of those strategies to apply to these different kinds of data. So first, I would never recommend using production data for transactional data testing. We want to generate all of that within the scope of automated tests. That gives us more opportunity to parallelize these things, to keep them into control, and to test the awkward corner cases. So we don't want to use production data. We also don't want to use versioned test data because we want our tests to be atomic. We want to be able to run them in parallel with one another and not interacting. So we don't want to be sharing data between the test cases. Next, reference data. Again, we don't want to use production data because it's too big and too heavyweight. Mostly, it makes sense to generate this sort of data again within the scope of a test. But there are some circumstances where it can be useful to use versioned test data. If you think about reference data, imagine a postcode lookup or something like that, then the real production data is probably going to have millions of records in it. But the advantage of this kind of reference data is it's nearly always read-only. So if we did provide a data set that was shared between test cases, there's not going to be any clashes in the test cases because they're never going to be writing to this reference data. So we could use maybe instead of millions of records, we could maybe have 50 records in our version test data that are deployed with a test in a test environment and shared between test cases in a read-only fashion. And last of my three groups is configuration data. Strangely, if you're not very familiar with continuous delivery, this might make you feel a little bit nervous. I would advise using production data for configuration data. We would like to be able to evaluate configuration changes as well as any other kinds of changes. So ideally, the configuration of our system in a test environment is as close to the production system as we can possibly allow it to be. There might be some weird kinds of tests where it makes sense to generate some versions of the configuration data within the scope of a test, if we're testing the configurability of the system, for example, but mostly not. And the version test data, there are going to be some kinds of data in a test environment that we certainly don't want to use the production version. We don't want it talking to the real instance of the production database, for example. We don't want real secrets deployed in a test environment. So we want to override those values using versioned test data local to a particular test environment as part of our configuration data management. So if we're losing transactional data, we're going to test those kinds of changes. Those are best done by creating a domain-specific language to describe test cases, encoding parameters in the test data for that domain-specific language, and use the DSL to establish the start conditions for a test case and optimize your application to make it efficient. and use functional isolation techniques to separate test cases. If you would like to understand a little bit more about what some of the jargon on this slide is talking about, I have a conference presentation which you can look up. If you look at my name, Dave Farley, and automated acceptance testing, acceptance testing for continuous delivery, you'll find a conference presentation which I gave to, given at a couple of GOTO conferences, that describes this approach that's on the screen there in a bit more in significantly more detail. Reference data, so treat like transactional data. We can do that kind of thing, or we can establish a minimal shared set because it's read-only. And then thinking about manual testing. So we want to be flexible. We want people to have control. We want to provide mechanisms for testers to quickly establish a given state without them sort of doing lots of manual intervention to get into that state. So using the acceptance test domain-specific language can be very powerful to allow manual testers to get the system into a known, understood state before they move forward to do whatever it is that they want to do. Reference data overrides can also work in this context to manage this kind of stuff. Performance testing. I think some kinds of performance testing need realistic scenarios, and it's worth thinking about recording production interactions and replaying them if that's at all possible, given the system architecture. The other alternative for less performance critical systems maybe is you can again use the acceptance test domain specific language to establish conditions and represent the scenarios that you would like to measure the performance of the systems for. Migration testing. At the point of release, your automated deployment systems should migrate your data. That one way or another using one of these patterns. This needs to be tested. After all, it's your production data. So take a copy of the production data at regular sustainable intervals in a test environment. Copy the processes. The copying processes of this data should be automated. Make the data anonymized if that's appropriate in your environment, and then every time you deploy a release candidate, use that copy of the data as a starting point to check that within your deployment pipeline that the migrations work, and then you can do some simple smoke tests to just check that that version of the system looks sane as far as you're able to tell. So kind of lightweight tests. So I've covered a fair bit of territory. If I'm honest, I haven't seen anything specifically about the data migration patterns that I've described written down yet. There's stuff on the other aspects that I've talked about. Certainly the deployment time migration stuff is described and talked about in my continuous delivery book. There's some other stuff about some of this, the impact of some of this, and architecting for data migration in the practical approach to large-scale agile development. And the book that I would very strongly recommend to you is Refactoring for Databases by Scott Ambler and Pramod Sadlaj, which is the definitive work on refactoring techniques for data stores.